Live session alert. I'm doing a live stream where I will tell you how you can evaluate your retrieval augmented generation pipeline and also monitor it using Opik. For the entire tech stack, we will be using LangGraph, and the project that we will be building is Customer Service Chatbot using hybrid search by Qdrant miniCOIL. So check out this particular URL and join our Discord channel to stay updated. Welcome to this project playlist series where we will build projects around large language models and agents. In the first video, we will build customer service chatbot where we will utilize hybrid search using Qdrant miniCOIL. Now, what is this hybrid search and how do we build this? Let's understand the process. Whenever we are building retrieval augmented generation pipeline, we need external data. For customer service chatbot, the best external data is the frequently asked question. So in order to get the frequently asked question, we will use the web-based loader so that we can get the context, raw context from the website. And once you have the information of frequently asked questions, you have to chunk it. So now this chunking strategy can be based on the chunk token. It can be based on the headers that you have. So what you can do is you can have markdown based splitting where you can split based on the headings. And now comes the interesting part. When it comes to hybrid search, you need to convert your raw data into embeddings. So we have two kind of embeddings. One is the sparse embeddings and one more is the dense embeddings. So in sparse embeddings, basically you're using keyword search. Based on the frequency of the occurrence of the keyword, you're doing the search. But when it comes to dense embeddings, based on the semantic understanding, you do the search technique like cosine similarity, and then you're getting the search results. So now what you need to do is, whenever you have a raw text, you need to convert that into embeddings by both sparse embeddings and dense embeddings. And once you have both of these two things, you have to save it in a Qdrant store. Now here if you notice, you have a very nice looking keyword called miniCOIL. So in order to understand miniCOIL, you need to understand what is sparse embeddings and what is dense embeddings. So let me quickly show you some examples so that it makes sense, right? I have two different documents. Let's say you have document 1 and then you have document 2. And in this document 1, I have a data which is mainly related to bank, which is financial bank. The bank offers financial services to customer. Now in my document 2, I have something related to nature. I sat by the river bank watching the sunset. Now if you notice in my document 1, it is something related to financial. Now in my document 2, I have something related to nature. Let's suppose you have a user and this user writes a query that is related to financial institution. Now it makes sense whenever user asks this particular question, you need to retrieve the document 1 rather than document 2. So how do you ensure you are retrieving the relevant information? This is where you convert that into embedding representation. So embedding representation, mainly you have it in two forms. You have dense embeddings and one more you have sparse embeddings. In dense embeddings, we are mainly using vector search, and in sparse embeddings, we are mainly using keyword search, which is mainly dependent on frequency of occurrence. Now what happens in dense vectors is, let's suppose you have document 1, you need to create document 1 vector. Same goes for document 2 vector, and then you have a query vector. So you have three different embedding vectors. Now if you look at all these three vectors, it will be of the same length. It's a fixed length. Whenever it comes to vector search, you will have a fixed length of the embedding vectors. So I'll just write some random value 0.2, 0.9, then minus 0.1, so and so. So now let's say this length is of 384. My document 2 will also have 384 length, and same goes for query vector as well. There is no change in the vectors value. So now that you have your document 1 vector, document 2 vector and query vector, the next thing is you will identify the similarity in your document 1 and similarity in your document 2. So how do you find the similarity? Just by using cosine similarity. So you'll use cosine similarity between your query vector and your document 1 vector. So this will give you some value. Let's say you'll have 0.8, and then again you'll use cosine similarity and you will just give your query vector, and then you have to give your document 2 vector, and this will return somewhere around 0.2. So higher the value that you have, higher the similarity it is. So based on the data that you have, you will get this particular similarity score, right? So this is your vector search results. Higher the rank, better the search results. Alright, so now that you have the basic understanding of how dense vector works, the next thing is you need to identify or understand how sparse vector works. Now that you have some basic understanding of dense vectors, let's understand sparse vectors, right? So sparse vectors is a bit different than dense vectors. In dense vectors, if you see, every single vector that you have has a fixed length and it is varying values, like you have 0.2, 0.9, you have decimal values. But when it comes to sparse vectors, either it will be 0 or it will be 1. So this one is considered as non-zero occurrence. So you have one famous search algorithm called TF IDF. So here you have two different terminologies. One is TF, which stands for term frequency, and then you have IDF, which stands for inverse document frequency. So now let's understand how this term frequency works. So here you have two keywords. One is TF. So TF basically it happens on the term that you have within the document. So T is nothing but the term, which is also referred as word. And in the given document, how many times is this T occurred? You just have to count of T comma D. But now when it comes to IDF of your term, it is basically a log of 10 of n divided by df of t. So here n is nothing but the number of documents you have, the total number of documents in your data, or you can also refer this as corpus. And then df of t is nothing but your document frequency of the given term or a word. So now that you understand what is TF and what is IDF, you need a better keyword search for sparse vectors. This is where we introduce a concept called BM25. So BM25 basically is your ranking algorithm for your keyword search. So now this is the formula. Now if you notice, you have IDF, which is nothing but your inverse document frequency that you are calculating earlier, and then you have F of t. So you don't have to confuse with the F of t, because this is again TF, which stands for term frequency of the document, and then you have a new parameter called K of t. So K of t, it's like saturation parameter for, it's a saturation parameter for your TF. Basically it's a value which is 1.2, and then you have B. So B is your length normalization parameter, length norm param, which is basically somewhere around 0.7, or it can be 0.8. And now you have this DL. So this DL is nothing but your document length. So if I have to calculate the document length of my example, let's suppose this is the example. You have 1, 2, 3, 4, 5, 6, 7. Then you have 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is your, did I count it correctly? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this is your document length 9, and this is 7, right? And now once you have the document length, you also need to calculate the average document length in the given corpus. So once you have all these details, this is where you have your BM25. So now what you need to do is, first thing is you need to calculate the number of documents that you have, which is nothing but your n. So if you notice the formula of IDF, you need log of 10 then you have n divided by df of t, which is your document frequency of t. So your n is nothing but 2. Why? Because I just have 2 documents. And now next you need to calculate the average document length. So your average document length is nothing but 7 plus 9 divided by 2, which is 8, right? And once you have this, you also need to have a document length. So in our case, the document length will be, I'll just assume it to be 8. Okay. So document length is also 8 and your average document length is also 8. But in most of the cases, these two things will be different. This you can define based on a fixed size, you can define your document length. Now the next thing is you need to define your f of t. So f of t is nothing but your term frequency for the given term and the document. Here the term, there are only two terms, one is financial and one more is institution. So if I want to calculate it for financial, how will I do it? So you just have to calculate count the financial in the document 1. So it should be 1. If you notice, the bank offers financial service to customer. So this financial is occurring only once. So here your term frequency is nothing but 1. So let me just add this equals to 1. And now you have count of institution in your document 1, which is 0. Similarly, you can calculate it for the other document as well, which is financial in document 2, which is 0. Then finance institution in document 2, which is again 0, because both the keywords are not present in document 2. And now once you have your frequency term, the next thing is you need to have IDF. So IDF, again you have to calculate for financial and you have to calculate for fusion. And here you just have to add log of 10. Now what is n? N is nothing but 2, which is the number of documents. And what is the term frequency of institution occurring in document 1, which is 0. And this will be undefined. Or you can also represent it as 0. Now when it comes to IDF of financial, it is log of 10, 2 divided by 1, which is log 10 of 1 will be somewhere between 0 to 0.5. Mostly it should be 0.3 or 0.4. So now you have the IDF value for the given document 1. Now once you have IDF, you just have to substitute in your BM25. So you just have to keep this in mind. Whenever you have high value of your IDF, that means it is very rarely occurred. If it is low value, that means it's a very common keyword. And when it comes to BM25 is your high, that means you have to rank the particular document. So you just have to substitute all the values. So this is how your sparse vector is calculated. Either it will be 0 or it will be a non-occurring 0 value. Alright. So now let's proceed again with our diagram. Now if you come to this miniCOIL, what is it? So instead of just using term frequency in BM25, you are also using vector search. So this vector search is nothing but your dense vectors, where you are getting your similarity scores. So you have a very nice blog article which is written by the Qdrant team. You can notice this particular diagram. The main idea is you have to use BM25 along with a vector search. So this is where in our entire project we will develop how you can use vector search and as well as keyword search using miniCOIL in order to set up your hybrid search approach. So this is where you have your data ingested. Till here, whatever you are doing is you have your document, you are saving it in a vector DB. Once you save it in a vector DB, this is where you trigger your retrieval augmented generation pipeline. So you have the user. So let's suppose you have the user, and here we will be using LangGraph in order to implement this. So we have to define a state graph. So this state graph will again be monitored with Opik, which is nothing but your tracing and monitoring system. So mainly if you are trying to learn LLM ops, this is where tracing and monitoring your entire RAG pipeline is also very important. So in our entire project series, we will be tracing our entire pipeline. So now that your entire state graph, which is nothing but your RAG orchestration, is monitored, you have to use your hybrid search. So now let's suppose user asks a question, which is financial institution. You're doing hybrid search from a vector store which is already saved. So your data is there, you're converting it into embeddings, you're saving it in a vector store. Once it is saved in vector store, you are retrieving the information, right? So user asks a question, from the saved document you are retrieving the information. So once you have your data, based on the data, you have to rank which is the most relevant document that has to be given to the user. So this is where we can use search like MMR, which is maximum marginal relevancy. Once you have your final 4 documents, you are giving it to the context, which is nothing but retrieval augmentation. In augmentation, you get the context, you get the user query, you are creating a prompt template. This prompt template is given to DeepSeek R1, which is your large language model, which will generate the final response. So you're retrieving information from vector store, you're augmenting your prompt with both context and user question, and then you're using LLM model to generate your final response. So this is gonna be our entire project approach. So now let's proceed with the code implementation. Alright, it's time for the code implementation. The first step is the installation. We will be using Qdrant client to save our embeddings inside a vector store. And then we have LangGraph. LangGraph basically is to build your entire RAG orchestration pipeline. And then you have fast embed. So basically you have your web pages to be a raw text. You need to convert that into embeddings. So this is where you need to have an embedding model for both sparse and dense vectors. And fast embed will help us to convert that. And then we have LangChain SambaNova. So SambaNova is a service where it provides faster LLM inference. So we will be using DeepSeek R1 model from SambaNova. And then we have LangChain and LangChain community. So basically you have to load your data and convert that into chunks. So this is where we will be utilizing LangChain itself, which is pretty compatible with LangGraph. And then we have Opik. So Opik is very important tool which will help us to monitor, trace, and as well as evaluate our LLM pipeline. Not just LLM, you have RAG and as well as agents pipeline, right? So Opik, in order to set it up, you need to configure it. And there are 3 different ways you can configure it. So once you run this command, it will show you those 3 ways you can deploy your entire pipeline. You have Opik Cloud, then you have self-hosted, and then you have local deployment. I will go with cloud because it's pretty easy to monitor your entire pipeline. So I'll just write 1. And now if you see, it helps us to add our API key. And in order to get our API key, you can just click on this URL, which is nothing but comet.com API. And once you click on this, it will probably tell you to create your account. Either you can connect it with your GitHub or Gmail account. And once you create your account, you will have this page, which will have your default API key, right? So I'll just copy this key. I'll come back to the collab notebook and I will paste it. So now it will create a root directory folder inside which it will save the config file. So here, if you notice, it is also asking for the workspace. If you are connecting your GitHub account with Opik, your username is the workspace. You can either create a new workspace or you can use the existing one. So what I need to do is, I will just use the existing one. If you have created a new workspace, you can use the new workspace. If not, you can use the existing one. So I just said yes, and now it will create the config file, right? And now the first step is, I want to define my 2 embedding model, which is a sparse and as well as dense. So for the dense vectors, I have the NLP or GTE large, which is mainly used for vector search, right? So we have used this a lot in our previous RAG tutorial as well, right? So I'll just run this dense embedding model. And then for sparse, I'll be using miniCOIL. So for miniCOIL, you just have to use Qdrant, miniCOIL version 1. So both of this will load the model locally. So as you can see, it will load the model locally, and once it loads locally, it will show the tick mark, right? And now the next step is, we need to get our external data. We'll go along with our flowchart that I showed you earlier. We will start with our external data, then chunk it, then convert that into embeddings and save it in a vector store. All right. So now I'll just run this. You have LangChain community from which you're using the document loaders. And from there, I need to pass the web page where I have frequently asked questions. And then using recursive character text splitters, I will split it based on the token size. So now I need to add my API key and as well as workspace. So I'll quickly use this particular collab secrets. So in collab secrets, if you notice, I've already added Opik and then I have my API key. So in order to use that, you have these 2 lines of code. So I'll just copy this. I will paste it here. So instead of secret name, let me close this. So instead of secret name, I'll just add Opik. So Opik is nothing but whatever I've saved here. So if it is SambaNova API key, you just have to enable SambaNova API key. If it is Qdrant key, you can use Qdrant key. In my case, it is Opik. Everything is in capital. It's simple. It's your key is saved there. You're just reading it. That's it. I'll just write import OS as well. Okay, import OS is already imported. And now I'm getting my API key, and workspace is nothing but this particular keyword, which is nothing but my username, Lucifer TRJ. So once this is done, we just have to run this and it will tell you whether you need to grant access or not. I'll just tell grant access. And now I have this particular page from Google. So if I open this particular page on a different screen, as you can see, it's a FAQ page from the Google account. You can use anything. You also have Shopify, right? So you have Shopify FAQ page. I'll just search for Shopify FAQ page. So if you see, you have a FAQ page of Shopify. So let's better use this particular URL because you have more questions over here, right? So I'll replace this with Shopify. And now you just have to use web-based loader. And once you have your URL set up, you have to load the raw data. So now your raw data is inside documents. So if I just print length of documents, it should be 1. It's 1. So now if I just write documents, 0 of page content, you have to see your entire data. So if you see, you have the entire data which is available on web page. Now we have to chunk our data. So when it comes to chunking, we are using recursive character text splitter with 1000 chunk size and chunk overlap to be 0. So what chunk overlap will do is you're converting your data into multiple chunks. So one chunk, if you want the overlap in the next consecutive chunk, you can give chunk overlap. If you don't need any overlapping between 2 different consecutive chunks, you can keep it 0. If you need a value, you can give 100 or 200. But in my case, I don't need any overlap. And then you can just give chunks equals to text splitter dot split documents. So since your documents is a LangChain object, we have to use split documents and then documents. It's not a string, it's a document object, right? So now if I print this chunks, length of chunks, it will be 13, right? So whatever data I have in my documents, you're splitting that based on the chunk size. So initially I had just 1, now you have 13. So this will ensure you're not hitting the context limit of the model. Alright, so now that I have my external data, I also have a chunking approach, and I've also created 2 embeddings, which is sparse, where I'm using miniCOIL, and then dense, where I'm using the GTE large model. The next step is I need to save that inside a vector DB. So again, you have 3 different approaches to do this. So the first approach is you can use Qdrant Cloud. The second approach is you can use localhost of Qdrant client, where you have to use what you call Docker image and run that particular model. And then what you can do is you can use something called as in memory, where your entire data is saved in memory within your project directory. Once you delete that, it's gone, right? So it only exists within your project folder. And in our case, we will be using in memory. And now we just have to use distance. Then you have vector params and models. So this is particularly used to set up your hybrid search model, right? And then you have Qdrant client. So Qdrant client is nothing but you create a space and then you save your data over there, right? So let me run this. And now I'm creating a instance where this particular file will be saved. So the folder name is temp. Inside that, I'm creating a app folder. So I'll just run this. And now you need to define a collection name, which is very unique. Every single time your data changes, you have to change your collection name. Why? Because it's a very unique identity for your own data. And the entire process, right, when it comes to your data, then chunking, This has to be done only once. Next time your data is changed, you have to index it again. So that way, it is a system design approach, right? Your data should be indexed only once, not twice. And now once you have your collection name, you have to define your vector configuration. So why we have to do this? Because you need hybrid search. You don't just need a simple vector search and save your data. So this is where once you have your collection name, you have a client. Inside that client, you have to create a collection, give it a name, and then define both your vector representation, which is dense and as well as sparse. For the dense, I'm giving it a name, which is the NLP large, the same what I've used for model name. And then I have models, then vector params, and this is where I'm using cosine similarity. As I already told you in this approach, for dense vectors, we are using similarity document 1, which is using cosine similarity, and it has something called as fixed size. Here I have defined it as 384, but in the code I am defining it as 1024. And once you define your size and as well as similarity score, the next thing is you need to define your miniCOIL. So this miniCOIL is your sparse vectors where you have to give your modifier. So this modifier is nothing but IDF, which is used for search. So I'll just run this cell. So you have your vector representation of dense, then you have vector representation of sparse. All right. So this is where you have your keyword search and vector search. Now you have to define your model. So when you define your models, what we are trying to do is your raw data chunks will be converted into embeddings and then saved in a vector store. So far, you just defined your model. You didn't saved or converted your model. So now what I'll do is I am using the dense embedding model. Then there is a function called embed. From there, I am converting my text into embeddings. So if you see, you have your chunks. Now, how many chunks do you have? You have total 13 chunks. If you notice, you have 13 chunks. What I'm trying to do is I'm extracting the page content. For example, chunks of 0 dot page content. This is your actual text. You don't just have page content, you also have metadata, right? You have metadata. If you want to save metadata, you can also save it, but here it doesn't make sense to save metadata. So what I'm trying to do is I'm just embedding only my raw data, which is nothing but page content. So if you notice, for doc in chunks, for entire 13 chunks, only extract the page content, and once you extract the page content, convert that into embeddings using your dense embedding model and as well as sparse embeddings model. So I'll just run this. So this will take few seconds based on how long your data is. Once you have your embedding, we just have to save it. So now if I print dense embeddings 0 of shape, you will see 1024. So you can use 1, you can use 2, this will be fixed, right? Now if I just print this, you will see the decimal values, right? So now if I print this miniCOIL of 0, you will see a values and then you will see something called as indices. That means, let me tell you what this indices is. First of all, let me print the shape. Let me print the shape of it. So you have total 2 different objects. One is your array and then is indices and values. So I'll just copy this values, dot values, and then I'll write shape. So hopefully this should be correct. As you can see, it's 107, right? So now total you have 107. And in that case, where and all you have your values. So if you see, your 16 has some non-zero value, 17 has a non-zero value, 18 has a non-zero value, 30th index has a non-zero value, remaining is just 0, right? So this is where your indices and value denotes. So I'll just remove this. This was just for intuition purpose. Let me also check for 1 and 2. 1. So if you see, it's different size. miniCOIL 0 was 107. Then first index is 144. That means your dense has a fixed number of vector length, whereas your sparse will have varying length. So this is the difference between both the vectors. Now, once you have your embedding model, you have still not saved it. You just used your embedding model to convert raw text into embeddings. Now we have to save this embedding somewhere so that you can use it for search, right? So in order to save it, what we have to do is we have to use models from Qdrant client, and you have something called as point struct. So in this point struct, you have to define your vectors. Just make sure you have this particular keyword same. So if you notice, here you have B, NLP or GTE large, and then you have miniCOIL. So whatever configuration you have used while defining your collection name, just use the same keys, right? Copy the same key, paste it here. So you have two different vectors. One is the dense and one more is the miniCOIL. If you notice in the miniCOIL, you need as object, right? Because you have two different vectors over there. One is indices and one more is values. So just get as objects, whereas in dense vectors, directly pass the vectors. So this is what you have to pass inside your vectors. So if you notice, you have enumerate, you are using your dense embeddings, you are using your miniCOIL embeddings and the chunks. So get all those values and then use the payload. Inside your payload, you have to add your text data, which is nothing but your page content. Whereas in your vectors, you just have to define your embedding representation of this particular page content. So this is very simple. Define your vector, define your payload, which is nothing but your data, and then just append every single points. So this will take again some time. And once you create this particular instance, the next thing is you have to use upsert, define your collection name and define your points. So once you do this, your collection is saved. And you can also verify it. If you check your temp app, this was what you created in memory. You have collection, you have meta.json. Now if I use collection, you have something called as miniCOIL drag. This is your collection name. If you notice, this is your collection name. That means you have saved your data inside a vector store. So once this is done, you can now use a search. You had documents. Now it's time for user query. So user query, what I'll do is I'll take something from Shopify. How much does Shopify cost? I'll just ask this question. How much does Shopify cost? I'll use the query. Now what I'm trying to do is I'm converting the query vector. So if you noticed my entire flow, you have document vector, you have document to vector. So far we only converted document into vectors. Now it's time to convert our vector embeddings as well. So you use the same dense vectors. You have dense embedding model dot query embed, add your query, then query embed, add your query, and then you have two different query vectors, both for dense and as well as sparse. And then you can use prefetch. So in prefetch again, you have to use the same name that you have used earlier. So if you notice, you are using GT large and then miniCOIL, and then you are using models, that particular model name and as object. So this is where you have to pass your dense vectors. Now what it will do is, we are at this approach. So you ask a user query. Once you ask the user query, you are directly using the hybrid search. As of now, we are just testing this hybrid search. Then this user query will be passed to state graph, which will have this hybrid search approach. But before we can give it to the state graph, let's just test it whether it is working or not. So what I'm doing is I'm directly giving the user query to the hybrid search. Then it will search. So when it search, it will give us two different search results. One is from sparse and one more is from dense, which has a limit of 20. So if you notice here, from my dense, I have the limit of 20. From my sparse, I have the limit of 20. So this is where you are getting the search results. And then you can run the query point. In this query point, you have to give the collection name, then prefetch, and you're creating the rank based on your dense vectors. So now if I click on results, you have the limit of 4. And if I run this, you have your final results. So this is where you have your data. So now what we are doing is save your data, create the prefetch, and then search your query points. So when you search your query points, you have the limit of 2020, but I only need 4 top results. So this is where you can use results dot points, 0th index, payload get documents. So if I just run results points, it has total 4 documents. But what I need is I just need the payload. Inside payload, I need the document. This is the context which I have to give it to the LLM. So you understood the flow. I'll come back to this particular diagram. You have the hybrid search. You have this 20 limit of sparse, 20 limit of dense. You have the fusion re-rank for top 4 results. Then you have to give it to the LLM model, which is your augmentation. So I only have to give the payload, right? So I've got the payload. And once you have the payload, I'll check the health. So Opik, I'm just checking if Opik is active or not. So if you see it's an active, you have your configuration file inside root, and then you have your API key, and then there are tons of other configuration, which means it's active. Now we will define our RAG pipeline. You know how to save your data into vector store, and you have also tested a simple user query. Now what you have to do is you have to define a state graph from LangGraph. So I'm defining a language model which is chat SambaNova cloud. Then you are defining your graph, which is nothing but your state graph, and then document. Why document? Whenever you are using the text, it is a simple string, but when it comes to LangGraph, you have to convert into LangChain document. So this is where you are using the simple string, converting it into LangChain object. And yeah, this is again a simple typing extension. And now, in order to trace and monitor your entire RAG pipeline, you have Opik, which has multiple integration, whether it is LangGraph, Llama Index, LangChain, or any other framework, it has integration for that. If you notice, you have LangChain, you are importing the Opik tracer, which will trace your entire pipeline. Here you have your system prompt. Since we are using DeepSeek model first it has to think, then it has to generate the response. So if you notice, you are an expert QA assistant, you only answer question which is from the context. If not, just say I don't know. That is your instruction, and it always has to structure the response between think tokens and close the think tokens. Then you have to have your final response, right? So this is my system template, and then in user template, I have to give the context which is been extracted from Qdrant, and then you have the user query, which is nothing but whatever the user asks the question. So this is where you are creating augmentation. First retrieve, which is nothing but your query points, then augment, and then generate. Now we just have to stitch everything inside a node of LangGraph. So I am defining the LLM. So if you notice SambaNova API key, how can you get that? You just have to open cloud.sambanova.ai, and then you have to create the API key. As you can see, create API key, give it a name, and once you give it a name, it will give you a new API key. And I've copied that key and I've saved it inside user data.get. So if I open this, as you can notice, I have SambaNova API key. I just have to copy this and paste it here. My keys is already saved inside collab secret keys. I'm just reading it from there. So now if you notice, the model name is DeepSeek R1, and then I'm defining the other parameters, which is temperature and top peak. Now that my LLM is defined, the next thing is I have to define a state. So my state will only define three things. One is the user question, the context that I'm getting from Qdrant, and the final response. I have to keep this in my state. So once you do this, I'm defining my search. So now if you look at the search, we already did this. So whatever you have it here, your client query points, collection name is same. So inside your search, what you have to do is you have to define your search results and as well as your documents, and then you just have to return the context. Once you return the context, you have to load that context from the state. So if you notice, in your state you have the question, you have the context. So your first node is search. So the search already has the context. If you notice, you're returning a dictionary which has context. You have to read that state inside generate. So what will generate have? Generate will have the context and as well as the user question. So now you have your context, then you're just creating a template. Inside this template, you have your system prompt, you have to give your context and as well as the user query. So there are two states. One is the context and one more is the question. Then you are generating the response from LLM, which is your third state, which is nothing but your answer. So now you have search, you have generate, you just have to combine this using a node. So now if you see, I'm defining a graph. So this graph, I'm adding two sequence. This sequence is nothing but your search and as well as generate. And then you are adding the edge. You have to start with search. And once you start with search, you just have to compile. And now in Opik tracer, if you notice, I have to define Opik tracer where I have to define this graph. And once you add Opik tracer to your graph, you can track your entire pipeline. So I'll just run this. And now response graph invoke, give it a user query, and once you give the user query, just add your configuration, and inside configuration you have callbacks. In this callbacks, you will need to add your Opik tracer. So just run this cell. So this is where you will have your final response. First it will search and then it will use generate. And what it will do is it has created a logging traces to a default project, and this project is saved at this particular URL. So you just have to click on this URL. It will open your dashboard. So now in this dashboard, if you notice, you have asked this particular question. So the question is nothing but how does Shopify cost? And then you have your think tokens. And once the think token sends, you have your final response. So if you notice the LLM model, you have the context. And in this context, you have the content that you're fetching. So if you notice, this content is where you're getting from the context. And then you're using your question. So if you see the question, how does Shopify cost? So this is the question. So based on this, you're tracking your entire node on LangGraph. So this is what we will do in the live stream as well, where you'll build the entire hybrid search platform. And once you build your hybrid search RAG pipeline, the next thing is you will use monitoring to track and evaluate your LLM model. So now if you notice, you have your final response inside response answer, and this is your entire response, right? So what we have did is we have built the hybrid search platform. The next thing is, in the upcoming video, we will build the evaluation pipeline for the given code. So stay tuned and don't forget to subscribe now.